Let's discuss 5 problems from the latest Codeforces round, starting with division 2b. You can read it now or listen to my explanation. In my explanation, you are given a permutation of length n. You need to find the largest integer k, such that you can sort this permutation by only swapping the pairs of elements with distance of exactly k. Let's consider an element on position I. Its eventual position must become ai in the end. But if we only swap pairs with distance k, the position of this element can change only by a multiple of k. So the distance between I and ai must be divisible by k. And that is true for all I from 1 to n. So if we only consider such constraints, the largest k that we can choose is the greatest common divisor of all such values, I minus ai. But it's pretty easy to see that if we take k equal to that GCD, then it's always possible to sort the permutation, because you can just use bubble sort. So consider the value 1 and swap its way to the very first position. Then consider the value 2, wherever it will be after the previous iteration. You can always put it to the second position without ruining the prefix that you've already built, and so on. So let's look at the implementation. Read the permutation, find the GCD of all such values and output. Now the problem C, you can read it now and listen to my explanation. In my explanation, you are given two arrays of length n. You need to find the number of matchings between those two arrays, such that in each pair, the value from the first array is larger than the value from the second array. As the initial order of the two arrays is not important, let's sort them both in increasing order. Now we can build a correct matching with such simple combinatorial process. Fix the first value from the first array and choose a pair for it. You can choose a pair for it from the several first values of the second array. Suppose you could have chosen it from the first 3 values of the second array. Then for the second element of the first array, the number of elements of the second array with which you can pair it is no less than the same number for the first value of the first array. So if the first number had 3 options, the second number will have 3 or more options. Suppose it will have 5 options. Then regardless of what we have chosen on the previous step, we will always have 4 options on the second step. So we can choose any one of those. And if the third element has, let's say, 6 elements of the second array with which it can be paired, then on the third step of this process we will have 4 options, regardless of what we've chosen on previous steps. So if the ith element of the first array had ki elements of the second array with which it could be paired, then on the ith step we would have ki minus I minus 1 options, because I minus 1 of those elements were already paired with the previous elements of the first array. So the answer is just the product of such values. So let's look at the implementation. I read the two arrays, sort them, and for each value of the first array, I find the number of matching values of the second array, the values that are less than it. And I multiply the answer by this number minus I. It differs from the formula I've written because here I use 0 indexation instead of 1 indexation. Then I open the answer. Now the problem D1, you can read it now and listen to my explanation. Let's define an operation that we can perform on the array of integer values. The operation is take the subarray of this array and sort it. And the cost of such operation is equal to the length of the subarray minus 1. Now the cost of the array is the minimal total price in which you can sort this array using such operation. you are given the array of length n, you need to find the sum of costs of all its subarrays. All of the values in the array are different. First of all, let's learn to sort the array in the most optimal way using this operation. Suppose that every point is an integer value of the array. Let's call a pair of elements where the left element is larger an inversion. Let's note that each inversion must at one point be in some subarray which we choose for the operation, because if it's not, it will remain an inversion in the final array. But if it's at some point taken into the same subarray which we choose for the operation, then this inversion breaks and it never returns back. So the order of those two elements stays correct until the end. So now if you draw all the inversions, your task is just to cover each one of them at least once. Now let's suppose we've drawn some number of arrays to cover those inversions. I claim that if you have intersecting arrays at some point, you can replace them with such one operation. All inversions that were covered by those two operations will be covered by this operation also. But the total cost of those two operations was the length of this one plus the length of this one minus 2. And as they intersected by at least one element, it will be less or equal than the length of this subarray minus 1, which will be the cost of the new operation. So it's never worse to use such operation instead of those two. But if the two subarrays which were chosen for the operation at some point are located right next to each other, then it's better to keep them this way instead of replacing them with such operation. So the best way to sort the array using such operation is just to highlight all such areas of connected inversions. And if we have a value which is not part of any inversion, we can also use it for the operation, because the cost of such operation will be 0 and it's not important. So let's just, for regularity, also do this operation. In such case, the total length of all subarrays used for some operation will be exactly the length of the whole array. So the total price of all operations will be the length of the array minus the number of operations that we've made. And the number of operations that we'll use is just the number of gaps between the two neighboring elements of the array, such that there is no inversion covering this gap. Plus 1. So the number of operations is the number of gaps plus 1. So it turns out that the cost of the array is equal to the length of the array minus 1 minus the number of gaps, not covered by any inversion. Let's separately find the sum of this term over all subarrays of our array, and separately find the sum of all those terms. If the length of the array is n, then it will be n minus 1. If the length of the array is n minus 1, then it will be n minus 2, but there are two subarrays of such length, so we need to multiply it by 2. And then there are three subarrays of length n minus 2, so 3 times n minus 3, and so on. In the end, we'll have 1 times n minus 1, because there are n minus 1 subarrays of length 2. Let's write it down as sum from 1 to n minus 1, n minus I times I. So it's equal to n times I, sum from 1 to n minus 1, is just n times the sum of I from 1 to n minus 1, which is n times n minus 1 over 2, minus the sum of squares of I from 1 to n minus 1. The sum of squares is a well-known formula. It's equal to n times n minus 1 times 2n minus 1 over 6. So let's put n minus 1 under the brackets and n also under the brackets, and we get 3 times n minus 2n minus 1, minus 2n plus 1. And we get, finally, n minus 1 times n plus 1 over 6. Now we just need to take this value and subtract from it the number of gaps that are not covered by any inversion over all subarrays of our array. So, more formally, we need to find the number of such triples of M, L, and R, where L is the left inclusive border of the subarray, and R is the right non-inclusive border of the subarray, and the pair M, M-1 contains a gap not covered by any inversion. So it means that the maximal element in the semi-interval from L to M is less than the minimal element in the semi-interval from M to R. And R can be N in that case because it's an uninclusive right border. First, let's discuss a squared solution. My solution was just first to fix M, then to iterate L from higher L's to lower L's, and keep track of the maximum on such semi-interval, and also keep track of the maximum R that I can use with such M and L, because if some R is valid, then all previous R's are also valid, because the minimum on smaller semi-interval is always larger or equal than the minimum on a larger semi-interval. And we can notice that as we go with L from higher to lower L's, the maximum gets bigger. So the maximal R that we can use with such L gets smaller and smaller, because we need the minimum to be also bigger. So we can simply use the two pointers method to keep track of the last correct R. To quickly know the minimum on such semi-interval, I simply precalculated the minimum on every semi-interval. Let's look at the implementation. I read the array A, I calculate the minimum on every semi-interval, I use the formula to find the sum of length minus 1, and then I want to subtract the overall number of gaps over all subarrays from it. I fix M, initially R is equal to N, and the maximal element on the left semi-interval is negative infinity, because initially I didn't consider any elements. Then I consider L from M-1 to 0, update the maximum on the left semi-interval, and while the maximum on the left semi-interval is larger than the minimum on the right semi-interval, I subtract R, and now all the valid right borders are located on the semi-interval from M non-inclusively to R inclusively, so the overall number of correct right borders for such M and L is R minus M. And then I output the answer. The hard version of the problem is exactly the same, but in this case you need to come up with a solution faster than n squared. I will tell the truth, I did not come up with it myself, so I had to look up the comment section, and actually this guy had the best solution, so I'll leave a link to his comment in the description if you would like to go and upvote him. But now I'll just explain his solution in my words. The main trick is to, instead of fixing M, fix the position of the maximal element on the left semi-interval. Let's call this position I. So all elements from the right semi-interval should be larger than this maximal element. But all the values from this semi-interval should be less than this element. So we can note that there is only one M that fits such I. It's the first element to the right of I, which is larger than I. Or such element cannot exist, of course. But if it exists, then it's the only fitting M for such I. And now an L fits such I as long as it is less or equal to I, and all the values from L to I non-inclusively are less than the ith element. So to find the smallest fitting L for such I, you just need to find the closest to the left element which is larger than the ith element. If it exists, then its position plus 1 is the first fitting L for such I. If it does not exist, then 0 is the first fitting L. So suppose there exists a matching M for this I. Then R fits this M and I, as long as all elements from M to R non-inclusively are larger than the element on position I. So the largest R which fits such M and I is equal to the position of the first element starting from M, which is less than AI. If such element doesn't exist, then N is the largest fitting R. So for a specific I, we need to be able to quickly find the closest to the right larger than itself, the closest to the left larger than itself, and closest value to the right starting from some position which is less than it. All of those can be done using segment tree in all of log time, but there is a simpler way to do it without using the segment tree. First of all, let's deal with the largest fitting R. So it's the first element starting from some position which is less than AI. In order to quickly find it, we will simply consider AI not in order of I, but in decreasing order of value. And let's keep a set of positions of those elements which we did not consider yet. So it will be a set of positions of those elements which are less than our element. And now to find the first element starting from some position which is less than AI, you can simply do a lower bound in this set of positions of elements less than AI. And we can use a similar approach to find the closest to the right and to the left larger than AI. We will keep another set which will contain on the contrary those positions that we've already handled. So it will be the positions of elements larger than AI. And using a lower bound through this set, we can find those two elements. So let's look at the implementation. I read the array A. B is an auxiliary array which will help me consider the elements in the decreasing order. Then the unused is the set of positions which weren't considered yet, and the used is the set of positions which were already considered, and I insert two auxiliary positions into it, -1 and n. So that there is always some position to the left of I and to the right of I. I initially set n's to this, and I consider the elements in decreasing order. The current element is on position I. So I erase I from the set of unvisited positions, and I find the next larger element and the previous larger element using a lower bound through the set used. And then I insert I into the set used. I set m to next larger, but if it's equal to n, then the next larger element does not exist, and I should skip such I. Otherwise, the maximal correct R is this, and the minimal correct L is this. If previous larger does not exist, then it will be -1, and the minimal correct L will be 0, which is also correct. Now all the correct L's lie on a segment from minimal L to I inclusively, so the number of correct L's is I minus minimal L plus 1. And all correct R's lie on a semi-interval from M non-inclusively to maximal R inclusively, so the number of correct R's is this, and I multiply and subtract it from the answer, and then I output the answer. And finally, the problem E, you can read it now or listen to my explanation. In my explanation, let's call a string good if it can be split into a set of palindromes of even length, maybe one palindrome of even length. You are given a string of length n. Find the number of good substrings of this string. First of all, we need to explore the definition of a good string. So once again, a string is good if it can be split into a set of even palindromes. I claim that we can use a greedy algorithm to find if the string is good or not. And the greedy algorithm is to always cut from the end of the string the smallest possible even palindrome. If at some point we cannot cut an even palindrome from the end of the string, then the string is bad. But if we cut the whole string at some point, then the string is good. So why can we always cut the smallest suffix which is an even palindrome? Suppose there are two different suffixes of the string which are even palindromes. Let's consider three cases. First case, the length of the smaller suffix, which is an even palindrome, is exactly the half of the larger length of the suffix, which is an even palindrome. In this case, this is a palindrome, and this is a reflection of this, so it's also a palindrome. So even if we used to cut like this, we could now instead use the same cutting, but now cut like this. So cutting this smaller palindrome will also lead to some correct cutting in the end. The second case is if the smaller suffix palindrome is less than the half of the larger suffix palindrome. Then if this is a palindrome, this is also a palindrome, then this is also a palindrome. And moreover, this is also a palindrome because it's centered at the same place where this is centered. So if there was some correct cutting with this suffix, then we can always use the same cutting if we cut this suffix first, and then this, and then this. So cutting the smaller suffix will also lead us to correct cutting in the end. And now the third case, if the length of the smaller suffix palindrome is larger than the half of the length of the larger suffix palindrome. Let's consider this center part of the larger palindrome. This is also a palindrome. But as this is a palindrome, then if we draw a suffix of such length, it will be also a palindrome, because it's the reflection of this within this palindrome. So in this case, we've proven that there exists even a smaller suffix which is also an even palindrome. Now, if it's larger than the half of the larger suffix, then we can use this operation once more. And we can use this operation to shorten the smaller suffix until it becomes shorter than the half of the larger suffix. And then we bring it down to one of the first two cases to prove that we could use a smaller suffix instead of the larger suffix. So now we have proven that if some cutting of the string uses not the smallest suffix, then it could also use the smallest possible suffix, which is a palindrome, and we could always transform it into some other correct cutting which uses the smallest suffix palindrome. Because we've actually proven a minute ago that the smallest even suffix palindrome will be no more than the half of any other even suffix palindrome. And then we can just reflect it and use such 3 or 2 instead of this one. Okay, so we've proven that if the string is good, then we can always cut the smallest possible even palindrome from the end of it. So for every position of string, let's find the closest to the left of it, such that they form an even palindrome, or find that such position does not exist. And let's draw an arrow into that position. So now if we choose some position to be the right border of our substring, which left borders fit such right border? To test if the left border fits the right border, we start going through those arrows, and we should arrive exactly into that position of the left border. Then the substring is considered good. So all the valid L's are located at this path of arrows. And if there's no palindrome with such right border, then let's not draw an arrow. But now, if this position as a right border had 3 valid L's, then this position as a right border will have 4 valid L's. So exactly the number of correct L's for this position plus 1. So this way we can very easily find the number of correct L's for every R, as long as we know all the arrows. So our job is to find for every prefix of the string its shortest suffix, which is an even palindrome. Our first step in doing that will be fixing a center of the palindrome, which is a gap between the 2 characters, and finding the longest palindrome with such center. In order to do that, I have used binary search by the length of the palindrome and hashes to check if such string is equal to such string. But there is some algorithm that does it in O of n and without hashes. You can find it yourself if you type into the search find all palindromes. But anyway, I've used binary search plus hashes to find the longest palindrome with each possible center. Now, all other palindromes that exist in the string are just smaller palindromes with the same center. if we only consider even palindromes, of course. So for each possible position of the center and the maximal palindrome with such center, let's draw a segment starting from the center to the right end of this maximal palindrome. And let's draw all such segments. Now, when I consider some prefix of a string, I can choose any of the segments that cover this position. For example, this segment gives me a palindrome with such right border and with such center. And this segment gives me a palindrome with such center. But as I need the shortest palindrome with such right border, I just take the segment with the largest left border that covers this position, and it gives me the shortest palindrome. So I can use the sweeping line method to keep track of all the segments that cover the current position. For all the segments that cover the current position, I store the set of their left borders. So to find where the arrow goes from this position, I just take the last element from the set and subtract the difference between that and I from I 2 times. If the set is empty when I pass through I, then there is no arrow going from I to the left. And then I will simply look at the number of correct L's for this position and say that the number of correct L's for this position is this plus 1. And then I just sum up the number of correct left borders for every right border, and that will be the answer. So let's look at the implementation. This is just the basis of the first hash, and this is the basis of the second hash. I use 2 hashes to pass the anti-hash test cases. This will be my hash, a pair of 2 hashes, and this will be my hash reversed. Is palindrome from L to R just checks that the hash of LR is equal to the reverse hash from n-r to n-l. This is because the reverse hash is taken from the reverse string, so the position of this substring is also reversed. This is the precalculation for the hashes. I read the string and I calculate the first hash, the second hash, then I reverse the string and I calculate the first reverse hash and the second reverse hash. And then I prepare to use the sweeping line method, and in order to do it, I create an array of lists where for each position I store segments that start at this position, and an array of lists which for every position stores the segments which end on this position. Then I consider a possible center of the palindrome, which will be a gap between the element I-1 and I. Then I binary search through the half of the length of the palindrome. So the half length which I know will result in the palindrome is 0, and the half length which I know will not result in a palindrome is minimum of I and n minus I plus 1, because such substring will be out of boundaries. And then until the 2 boundaries meet, I test the substring from I minus middle to I plus middle, and if it's a palindrome I move L to middle, otherwise I move R to middle. After the binary search, L will be the largest half length of the palindrome with such center. If L is 0, then such palindrome is empty, but if L is larger than 0, then I add a segment from I to I plus L into the event queue. I say that it starts on position I and ends on position I plus L. And in both lists I store the left border, because that's what I need to add into the set. And this left border of the segment is actually the center of the palindromes, which cover the current position in the set centers. And dp is just the number of correct L's for a given R. Then I consider different positions. After I consider this position, I need to update the set, add all centers for each segment that starts here, and delete a center for each segment that ends here. But before I do that, I check that if the set is empty, then there is no correct left borders for such right border. But otherwise, I find the largest value which is currently in the set, and I call it last. And I minus 2 times I minus last is where the arrow points. So the number of correct left borders for such right border is by 1 more than the number of correct left borders for such right border. And then the answer is just the sum of the number of correct left borders for each right border. And then I output the answer. That's it for today. Thank you for watching, and I remind you that I give private lessons on competitive programming. If you're interested, contact me on Telegram. Goodbye.